So if the compiler can find enough instruction level parallelism in the application, we're going to see what that means to the architects and what kind of architectures that would allow us to design. And the goal here is to design an architecture that actually can issue or can start more than one instruction each clock cycle. So another way to express that is that we would like to have a CPI, cycles per instruction, which is smaller than 1, or IPC, instructions per cycle, which is larger than 1. The trick we're going to look at now is called superscalar architectures. And here we're going to combine, in this slide here, we're going to combine static scheduling of the compiler, and later on we're going to take help from what's called out-of-order execution to also do dynamic scheduling to find enough instruction level parallelism. This is it's up to the hardware to find which instructions actually can be executed at the same time. So even though we rely on the compiler to do a good job at finding independent instructions, it's the hardware's choice to decide which of them are allowed to execute at the same time. This superscalar trick is implemented in all the processors, all the high-end processors around, and has been doing that's been the case for a long time. So your x86 processors in your laptops definitely are superscalars, as well as many of the processors in your cell phones. Later on, we're going to talk about what's called very long instruction word, VLIW architectures. Here, we're going to put a much even larger burden on the compiler. So the compiler has to be the one that finds independent instructions, but also guarantees that things are independent. We don't allow for any dynamic scheduling to happen in the hardware while it's executing. This was very popular in research maybe 15 years ago, 20 or 15 years ago. There's a surviving commercial implementation, IA64 or Itanium, which is a high-end processor that Intel produces. And also there was a really fun company called Transmera that in the beginning of 2000 started to release chips that competed with Intel for a while, and these chips were also VLIW chips. So we're going to build a superscalar pipeline, but before we go there, let's just remind ourselves what the single issue pipeline looks like. So that's actually the pipeline we've been talking about would be referred to as a single issue pipeline, where you start one instruction each cycle. So here we have a flow of instructions that being fetched from instruction memory. The program counter identifies which instruction to fetch. We fetch the instruction into a instruction register here. Then in the next cycle, we read the register file. The next cycle, the ALU will do its job. The next cycle, we will access the first level cache. It says DMEM here, but it's really the first level cache. We access, and only in the case of cache misses do we need to go out to the memory itself. And at the end of the day, the last pipeline stage, we write results back to the register file. And these were the pipeline stages symbolized at the bottom here: instruction fetch, instruction decode, execute, and address calculation, memory access, and write back. What we're going to do now is to combine several of these pipelines together. So at the high level of drawing this, what I'm showing here is that we have put two of these pipelines right next to each other, pretty much identical pipelines. These pipelines will fetch instruction from one sequential program. So we're not talking about the parallel program here. It's a sequence, like the instruction in our compiler example, the sequence of instructions. These two pipelines are not independent as it looks here. Actually, they share quite a lot of things. The most important thing that these pipelines share is the register file. So in the previous single issue pipeline, we had a single register file with 32 registers. Well, we also have a single register file with 32 registers here, only that these are now read in parallel with whatever instruction is being executed here and whatever instruction is being executed there. We have two independent ALUs that now can perform operations in parallel with each other. And then we write the result back to a common first level cache. So this first level cache is shared between those memory stages. And then both of the last pipeline stages will write results back to the register file. So what you see in front of you here is a Superscalar pipeline. It's a two-way issue Superscalar pipeline. The x86 processors that you have around you probably have more like a four-way issue Superscalar pipeline. So they would actually have four of these pipelines sharing the same register file, four different ALUs, and four memory stages sharing the access to the first level data cache. So as I said, this is a design that actually executes sequential instructions. So from the sequential instructions stream, the hardware will figure out which of these can be started at the same time. So for example, just playing a video here, these instructions will flow through this design here, and so we will get a good throughput, because theoretically we have now doubled the throughput of this pipeline. We can complete 2 instructions each cycle and get the cycle per instruction CPI value actually below 1 in theory. So if we go to the more detailed picture of what the pipeline looks like, I'm sorry to those of you who complained about the resolution of these pictures. You really have to watch these pictures using a large screen. So what you have here, I just cut and pasted 2 of these pipelines together, 2 ALUs, both pipelines sharing a common register file and some common access to memory or first level cache called memory here. What's really interesting thing in this design here is what's happening to the very left. So what we have in the very left here is we still have 1 program counter, and the program counter will point into the instruction memory, and here we will fetch up to 2 consecutive memory instructions. If the hardware deems that it's okay for you to start 2 instructions at the same time, these 2 instructions will be sent into each of their pipelines in parallel. That's interesting. We, as I said before, we have a shared register file between the pipelines, but now we need to support twice the amounts of reads and writes to this register file, because we need more read and write ports to be able to feed these 2 hungry pipelines with exciting values from the register. Sorry. Likewise, we have to supply twice the amount of read and write ports to the L1 cache, accessing the memory system, because we may have accesses from both of these pipelines at the same time. Interesting to note in this picture as well is that only the top pipeline may execute branches, because only the top pipeline has this extra logic required by the execution of branches, and only the top pipeline have a program counter. What a slight modification I made here is I said that the program counter is updated with either 4 or 8 each cycle. With that depends on whether or not you manage to launch 1 or 2 instructions into the pipeline that very cycle. So here you have it, the Superscalar two-way issue. But two-way issue also means that you will need twice the amount of instruction level parallelism in order to feed this beast with enough instructions that are independent of each other. The 5-stage pipeline that we're going to talk about in a assembler example here is a sort of specialized pipeline where we, in the top pipeline, so it's a two-way Superscalar pipeline, but in the top pipeline we can only handle integer ALU, branches, and memory instructions. In the bottom pipeline, we can only handle floating point instructions. And we assume, of course, that this is internally pipelined, just as I showed you before in the example, even though we execute some kind of floating point instruction that takes more than one cycle to complete, we can still start one new instruction every cycle. So this is internally pipelined. So this is it's called the Superscalar or the DLX architecture that we're going to use in the example on the next slide. So it's just to reiterate, we have a two-issue superscalar, so we can two instructions can simultaneously be issued in this architecture, but one has to be a floating point and one has to be an integer, because these two pipelines are specialized. So we can fetch 64 bits of instructions each cycle, there are rules here, of course. If we fetch 64 bits of instructions, we really hope that every other instruction is a floating point instruction and every other instruction is an integer instruction, because if we fetch two integer instructions that are put sequentially right after each other in the code, then this very superscalar pipeline is not going to help us much. And of course, we cannot, we have to obey this sequence nature that the programmer forced upon us. So we can only start the second instruction if the first instruction is issued. And of course, not even the first instruction may get issued, because there may be some data dependencies that forces us to hold that back. We also, as we already discussed, we need more read and write ports to the register file to make this execution happen. So what I'm showing you here is how a sequence of instructions, unfortunately, these instructions have perfect interleaving. The first instruction is an integer. The next one is a floating point instruction. The next one is an integer, next floating point, next integer, next floating point. So we're going to follow the life of 6 different instructions that are started throughout their life in this superscalar pipeline. First cycle, we are lucky enough that we can start 2 instructions because there was not any data dependence. And so they're going to now flow out. It's going to take them 5 cycles to complete. The very next cycle, we also managed to start 2 instructions. Once more, we have enough instruction level parallelism. No nasty data dependencies, no branch dependencies, or anything like that. And also in the third cycle, we managed to start 2 instructions. So this is how they're going to flow in the pipeline as a waterfall, integer and floating point instruction right after each other. So one thing to notice here, I said we need twice the amount of instruction level parallelism. Well, if you think about it, what it takes now for you, let's say that one of these instructions is a branch. Let's say that this instruction is a branch. The only reason that we didn't need to store the pipeline was that the very following floating point instruction is independent on this branch. And also, to fill the delay slot, we also needed to fulfill the requirement that this instruction is independent on the branch and this is independent on the branch. So now with a single delay slot of your pipeline, you actually have to find 3 independent instructions, not just 1 independent instruction as you did in the previous example. This is just one example of how the demand on ILP increases when you go to superscalar. If you would like to perfectly schedule your superscalar, you have to ask the compiler to do loop unrolling 5 times actually. And if it does loop unrolling 5 times, that means that you will be able to perfectly use the integer pipeline of your architecture. This shows cycle by cycle how many instructions you can start each cycle from our simple example code, if it's been unrolled 5 times. So first cycle we can start a load, which goes in the integer pipeline. Second cycle we can start a load. And first in the third cycle we can start to use the floating point pipeline, because that's the first time, due to data dependencies, that's the first point in time when we can launch that floating point instruction. And then we can launch floating point instructions the following 5 cycles. After we've done the 5 loads, we start to do the 5 stores, and now actually the data dependent, the read after write dependence between the top add and the first store, they are just pulled far enough apart to make sure we don't need any bubble in the pipeline. So it's perfect. It's the 2 cycles in between them. And then we can just fill the pipeline after that. So at the end of the day, with this superscalar, fairly simple superscalar pipeline, we managed to execute our example code, 5 iterations of the example code in 12 cycles. So that means 2.4 cycles on average for each iteration of this loop. So that's a new world record. So the limits to the superscalar execution, as you understand, is instruction level parallelism. In your machines, as I said, you have 4-way superscalars. So the amount of parallelism you have to find is rarely, very rarely enough to keep all those 4 pipelines going. Actually, the kind of the CPI number that you would get on your machine would still probably be very close to 1, maybe 1.5 on a good day. Even for fairly well-optimized pieces of code, even though you have a 4-way issue. So you're not getting that much bang for the buck, and what's holding us back is instruction level parallelism. And also the decoding becomes quite complex if you're going to leave it to the hardware to figure out when it's safe to issue many of these instructions in parallel. Hardware needs to do lots of data dependence analysis on the fly. And we're going to discuss a few of the tricks that the hardware may use to do the bookkeeping that's needed there. And also with a longer pipeline and a wider pipeline like this, the control dependencies are generally much more costly. So I already discussed about the delay slot and how much ILP you have to find. And if you don't find the ILP, then the cost for that branch is going to be more than twice as high than the cost for a single issue superscalar. So we need lots of techniques to find ILP. It's very important. We looked at a few compiler techniques. What we're going to look at further down the road is a dynamic technique. We're going to look at something called out-of-order pipeline execution that further is going to help us find ILP. And we're also going to look at a hardware-software co-design trick, which is used by the VLIW processors, where we're going to introduce new kind of expressiveness to the compiler people. We're going to allow them to perform pretty scary transformations, but we're going to provide the right hardware support so that they can make sure that those transformations actually are safe to do.